So, welcome everyone. This week we have Austin Gaffglione. Let me read your title out. Speaking to us about what was Lamplighter groups, and then Diestel-Leader graphs. Yeah.
Mm-hmm.
Okay. So it's all yours.
Okay. So let me share screen. Yeah. Okay, there we go. Okay, so today I'm going to talk about Lamplighter groups and Diestel-Leader graphs. And they are nice little constructions people might talk about in geometric group theory. But before we construct these, we actually want a motivation. Why are Lamplighter groups and Diestel-Leader graphs important? So we offer some motivation. With a question. And this question was proposed by Woess in the 1990s, and it's of the following. So he asks, this is credited by Woess, and is every nice, so every, so nice, I put in quotations, so I have to justify what nice means in this context. So every nice infinite graph, quasi-isometric to the Cayley graph of some finitely generated group. And when you look at this question at first glance, there's a lot to unpack, so I'll justify it. So by nice, it's a technical term. It actually involves three terms. So this nice means locally finite, connected, and vertex transitive. So locally finite means I don't have a situation where there's infinite number of edges connecting to one vertex. Connected, there's no isolated vertex. So any vertex is connected by an edge. Or if I have two arbitrary vertices, I can find a sequence of edges that connect them. And vertex transitive is something a little more technical, but it means that so vertex transitive means that automorphisms of this graph, so if we call it gamma, they act transitively. On the vertices. So if I have two arbitrary vertices, V1 and V2, for instance, I can find a automorphism of this graph that sends V1 to V2 and vice versa. Okay.
So that property seems, of the three, the most restrictive.
Yes. So vertex transitive, it actually has some very nice consequences because you can talk about the symmetry of a graph when a graph is vertex transitive. So if I were to zoom in into my graph at any point, it looks locally the same. So if I zoom in into two arbitrary vertices, the graph looks identical. And of course, this is when we're talking about infinite graph. In the case of a finite graph, of course, it doesn't really make sense if I zoom in into two vertices. And we also have this term quasi-isometric. So I should probably define what I mean by quasi-isometric. So I have a definition. So if I'm given two metric spaces, so x and d, x, and y and dy, and we say a map F, so F maps x to y, is a quasi-isometry if, so there's these two global constants, so I'll call them K and C. So K is understood to be greater than 1, greater than or equal to 1, and then C is understood to be positive such that for all x1, x2 in my space X, and for all y in my metric space Y, we have the following two inequalities. So the first one is going to be G minus so we have this inequality, and we also have a this inequality. So K times the distance in X between X1 and X2 plus C. And we also have this second property I should mention. So this is property 1 and property 2. And the second property is that I think it's the distance in Y is bounded by this K. So these are the two properties that define a quasi-isometry. If you know what a isometry is between two metric spaces, it's essentially that if two spaces are isometric, the distances are preserved. In the case of a quasi-isometry, the distances are not preserved, but rather they have this sort of additive and multiplicative bound between them. So you have this allowed variance between distances in your two metric spaces. And in this particular case, when we look at the Cayley graph of a group, we're taking the geometric realization of this graph. So we're imposing this distance with respect to some generating set of my group. Okay. So I've defined what nice means and quasi-isometric. And when I say a finitely generated group, I mean a group with, so any presentation of this group, or there exists a presentation of this group that has finitely many relations. So Woess proposed this question. So is every nice infinite graph quasi-isometric to the Cayley graph? So little typo. Of some finitely generated group. So
a question maybe that would make more sense to me. So is the converse, I guess, true? So if you have Cayley graph of some finitely generated group, but it automatically has these three properties, yeah? Or it is quasi-isometric too. What do I want to say? Okay, so if I have a Cayley graph of a finitely generated group, it automatically has it is a nice infinite graph, yeah?
I believe so, yes, but I could be wrong. Yeah, so the question is essentially asking, so usually, yeah, like we mentioned, in geometric group theory, I'm focused, so I'm given a group and I want to determine what its Cayley graph looks like in a metric space structure. This question is actually asking the reverse. So if I'm giving it a nice graph, does it always correspond to a nice group? And if you look at the first perspective, if you look in this perspective, you should think, yes, if I'm given a nice graph, it should correspond to a nice group. The answer is actually no. So I'll write answer and I'll just say no and leave it as is. We're done. But I'll adjust by this. So in, I want to say the early 2000s, two mathematicians, you might suspect, are Diestel and I.Leader. They conjectured that some of the graphs are not quasi-isometric to a finitely generated group. And this is what we're going to call the Diestel-Leader graphs. So I'll just write in parentheses Diestel-Leader. And while they constructed these groups, I think it was not verified until the early 2010s, so about 2 years ago, by these trio of mathematicians, I think Eskin, Fisher, and Whyte. They verified this conjecture that Diestel and I.Leader came up with. And before we could talk about the construction of a Diestel-Leader graph, we're actually going to talk about Lamplighter groups. So we will soon find out that after we construct these Lamplighter groups and we construct the Diestel-Leader graphs, we can find an isomorphism between the two graphs. And because the two graphs are isomorphic, so I should note that if two graphs, or so if I have something as quasi-isometric to another graph, if I change the generating set, I still have the quasi-isometry. So quasi-isometry is invariant under finite generating subsets or finite generating sets. Okay, so let's talk about Lamplighter groups. So there are two different perspectives I can take for the construction of Lamplighter group. I can either take an algebraic perspective, which is a little messy and not really easy to say, or I can take a geometric perspective. I'll actually mention both. So the first perspective is this notion of the Wraith product. So little typo. So I should probably define what a Wraith product is. So definition. So if I'm given that G and H are, I think for this notion of Wraith product, they have to be abelian. So given that if I have two abelian groups G and H, the Wraith product G and then this little squiggly mark H is, so it's this direct sum but indexed by elements in H of G, and it's a semi-direct product with H. So in a very weak sense, this is almost saying, this is the idea of exponentiation with groups. So I can think of this as G raised to the H. Of course, there's some technicalities and there's not necessarily an equivalence between two, but I can think of it like this. So in particular, as a nice example, the Wraith product of Z2 and Z is L2. And this is our Lamplighter group, or one of a specific case of a Lamplighter group. So I can define the Lamplighter group of I can define one kind of Lamplighter group like this. In general, if I take the Wraith product of Zn with Z, I get the general Lamplighter group.
So why the name Lamplighter?
That actually comes with the geometric picture. So
Okay.
I'll actually talk about that now. So we can also define it geometrically. So I'll define it with a Lamplighter picture. And in my opinion, this is the more fun perspective. It's easier to understand, and there's a lot, you can gain more intuition from this right away. So suppose I have this bi-infinite street, and I have a bunch of street lights. So I have this street light here, and it's bi-infinite, so it goes on forever in both directions. And each lamplight is indexed by an integer. So this circle that I drew with the vertical line going through it, I index as 0. And I index 1 is -1, -2, -3, and so on in the negative direction. And then 1, 2, 3 in the positive direction. And in this bi-infinite street, so you can think of it as a totally disconnected street, so indexed by C. I have this lamplighter, so this, you can think of it as this ominous figure that just starts at 0, walks to left and right, turns on bulbs. So maybe in this picture, it turns on the bulb at 1, 2, and then moves back to -1. And that's the final position of the lamplighter. So in every lamplighter group, our Lamplighter picture, I should say, we have two different pieces of information to encode. So we care about, so in every Lamplighter picture, so we care about the number of bulbs illuminated. And we also care about the final position of the lamplighter. And I'll abbreviate the lamplighter as just LL. So we want to encode two different pieces of information on the number of bulbs illuminated and the final position of the lamplighter. Of course, there are some initial conditions we have to worry about in this picture. So some conditions. So the first condition is lamplighter, so abbreviated as LL, always starts at 0. And then I also have that the lamplighter can only illuminate a finite number of bulbs. So I never have a case. So I call this finished picture a lamplighter picture. So I never have a lamplighter picture where, say for instance, all even indexed in bulbs are illuminated or all odd indexed bulbs are illuminated. I only have a finite number. Okay. Now I can talk about defining out, or I can give you an example of a lamplighter picture. So maybe another example is following. So I have this bi-infinite street. I have the bulb indexed at 0. Say -1, -2, -3, and so on. And then 1, 2, 3, and so on. And let's say in this lamplighter picture, I can have bulbs illuminated -1 at 0, and maybe the lamplighter's final position is at 1. And so in this case, so I have 2 bulbs illuminated, and I have the final position of this lamplighter. So the order of this so the operations needed to create this lamplighter picture, there are multiple ways. So the lamplighter could illuminate the bulb at 0, 1 to -1, and so starts at 0, or turns the bulb on, goes to -1, turns the bulb on, and then goes all the way to 1 and stays there. Or the lamplighter could illuminate the bulb at 0, goes to 1, and then backtracks to -1, turns the bulb on, and then goes back to 1. So we can actually encode this information from a lamplighter picture as an ordered pair. So I can encode it as H comma K, where H is a member of this bi-infinite direct sum with Z2, and K is an integer. So in this particular case, H encodes the number of bulbs illuminated, and K encodes the final position of the lamplighter.
So a question, I guess.
Yes.
Can he skip over? So it's a valid configuration, I guess. He illuminates 0, he illuminates -1, he illuminates -3, and then he ends up back where you did. So you can skip over lights.
Oh, yes, of course. So I can also have this picture where he illuminates 3, for instance. So the lamplighter illuminates the bulb at 0, goes to -1, illuminates the bulb, goes all the way to 3, illuminates the bulb, and then goes back to 1. So yes.
Okay. Interesting. Okay, keep going. That's
okay. So I can actually define the lamplighter group in this manner. So it's this ordered pair H and K. So I can define multiplication between these two elements. So if I have, let's say, H and K, and I multiply by, let's say, H prime, or yeah, let's call it H prime, and then K prime. So the way I multiply two elements is so h and h prime, I add the components of h, but then I add, so I'm gonna define this h double prime. And then I add k and k prime. So this h double prime, so every coordinate in this h double prime is just h prime shifted k units to the right or to the left, depending on whether k is positive or negative. So in this definition, we actually can observe the semi-direct nature of this, the product of two elements, because instead of just adding h and h prime, I have this shift in h prime, and I just call it h double prime. And of course, the way I multiply or the k's interact is what you might suspect. So I'll use an example to illustrate this. So suppose I have this by infinite street, and then 0, -1, -2, -3, and so on. And then 1, 2, 3, so on. And let's suppose that h comma k. So I'm representing h as this by infinite ordered pair, so it's a little tricky to write down, but let's say 0, 1, 0, 1. So I have to denote which index is the 0th index. So in this case, let's denote it as this entry right here, so the 0th index. And let's say k is 1. And then for h prime, k prime, let's say h is 0, 0, 1, 0. And let's say k prime is equal to -1. Okay, so in this Lamplighter picture, I first do h. So for h, I start at 0. I have illuminated bulbs at -1 and 1. And the lamplighter's final position's at 1. So now when I look at h prime, instead of starting at 0, the h prime starts relatively, so it starts at 1. So in this view, h prime starts at 1. And then, oh, so in this case, I should, this is going to be the 0th index for h prime. So now the lamplighter starts at 1 for h prime. Turns the bulb on again. So in this case, I should say we're working in L2. So bulbs are turned on and off. So if I turn a bulb on twice, it turns it off. So in this case, the bulb is off. And the lamplighter moves back to -1. So this is the picture of h comma k times h prime k prime. So this means when I multiply the two, I actually get something like this. So -1, 0, 0. So in this case, there's only one bulb on and it's indexed at -1. And so this is the 0th index. Or
So it should be 1 then, yeah.
Yeah, thank you. So yeah, so this is how I multiply two elements. So if you realize, because of the semi-direct nature of this product, it's not a billion. So if I were to first do h prime, k prime, and then do hk, I actually get a different lamplighter picture. Okay. So I can talk about a presentation for Ln. In this case, I'll just focus on L2. So focus on L2. Okay. So in my Lamplighter picture, I need two basic actions. I need two basic actions. So first, I need the Lamplighter to move to the left and to the right. And then the second basic action I also need is the Lamplighter to turn bulbs on and off.
So you are defining the alphabet, right? Of the,
Yes,
Yep.
yes. Okay. And so I can define the alphabet for this presentation of L2. So the first one, so for 1, I call it T. And then for 2, call it A. And so for example, if I have this T to the N, I'm really just saying the Lamplighter moves N units to the right. And then if I look at T to the minus N, the Lamplighter moves N units to the left. Okay. So in L2, so Lamplighter picture where bulbs only have 2 settings, on and off, I can first observe that A squared is equal to 1. So if I turn a bulb on twice, same thing as doing nothing. And I can also observe another idea. So I have this, so imagine the Lamplighter starts at 0. With no bulbs on. And then after the Lamplighter starts at 0 with no bulbs on, moves K units to the right. Turns the bulb on. So it's going to turn the bulb on at K. And then moves K units to the left. So when the Lamplighter moves K units to the right, turns the bulb on at K, and then moves K units back to the left, the final position is going to be at 0. So now the Lamplighter does the same. But with K replacing L. So L is some integer, and L is not equal to K in this case. So the reason I want to mention this is because if the Lamplighter moves K units to the right, turns the bulb on, moves K units back to the left, and does the same thing with L, except L is not equal to K, so moves L units to the right, turns on the bulb at L, and moves L units back to the left, so back to 0. I can interchange these 2 actions, and I still get the same Lamplighter picture. So this means that the commutator, so T to the K, A, T to the minus K, and then T to the L, A, T to the minus L, I should get 1. So conjugates and products of these 2 relations, so A squared is equal to 1, and then this commutator relation, they're equal to the identity. So this is all we need for the presentation of L2.
So you said, but maybe I just wasn't listening. So it's provided that K isn't equal to L, yeah?
So yeah, K and L are different.
Okay, okay. If they're equal, then you get what? Not one, but
One is one.
Yeah, yeah.
Yeah.
So that's a good idea. So if I were to draw it out, and I have 0, and let's say I have K. So when I first do K, I move K units to the right. So I shall highlight this. I move K units to the right. I turn the bulb on, and I go back to 0. And if L equals K, I just do the same thing again. So I turn the bulb on, and I get 0. So in this case, I turn the bulb on twice at K, so it turns off. So in
Okay.
L2, yeah, this is equal to the identity. But it's actually a good thing you mentioned in Ln, so when n is greater than 2, the bulb just stays on at a certain setting. So I think in Ln, yeah, this relation is still 1. Or when you compute this commutator, you still get 1.
Okay, it's just in when Ln is it? Well, I'll ask in a second. Keep going.
Okay. And so this is all we need for the presentation. So in fact, we get L2 is going to be isomorphic to presentation A and C. So A squared is equal to 1. And then we have this commutator relation. So T to the K, A, T to the minus K, T to the J, A, T to the minus J for all J and K. So I can write this a little bit better. So okay, so we actually obtained this presentation for L2. And in fact, we can generalize this. So we can generalize so Ln. So it's the same idea, except for the defined relation A squared is equal to 1. We replace it with 8 again. It's equal to 1.
So the n Lamplighter group is like the light has like n different colors, and after you turn it, n colors on, or maybe n different settings for the light. Or
Yes, you can think of it as n different settings. So the settings for the bulbs can range from 0, which is off, all the way to n minus 1. So 0, 1, 2, 3, all the way to n minus 1.
okay.
Okay. So we can also represent L2 as a group of 2x2 matrices. And okay, so L2 is a group of matrices. So elements of L2 can be represented uniquely. So I can represent elements of L2 uniquely as a pair H comma K. Where, of course, as we defined before, H is a bi-infinite direct sum of Z2, and K is an integer. We can also view H as a polynomial. So we can encode H so this polynomial P is going to have entries either 0, 1, and it's in terms of T and T inverse. So as an example, suppose that H is equal to this bi-infinite order pair. So 0, 0, 1, 0, 1, 1, 1, and then trailing zeros. This is going to correspond to a polynomial of the form p is equal to t to the -2 plus 1 plus t squared. So like instead of viewing h as this
So zero,
bi-infinite,
zero here is the
oh,
one right next to the one, yeah? So 1, 0, 1, and that one is the 0, yeah?
oh, I think, yeah, I should specify. So the 0th entry is going to be this, the first one from the 3 consecutive.
Okay.
So yeah, so t to -2, yes. Okay. So I can, instead of viewing h as this bi-infinite ordered pair, I can view this as polynomial with integer powers. So now I can instead view elements of L2 so instead of h comma k, I can view them as p comma k. Where of course p is this polynomial in Z2, or with entries from Z2 with in terms of t and t inverse, and then k is this integer that denotes the final position of lamplighter in every lamplighter picture. And then of course I propose the following, so proposition that L2 is isomorphic to this subgroup of the following 2x2 matrices, so t to the k, 0, 1, and then p, where of course k is an integer, and then p is this polynomial of entries from Z2. Okay. In the proof, I'll just give you the idea of the proof. So the construction of the map. So if I denote H as this subgroup of matrices, so T to the K, P, 0 and 1, there of course K is an integer, and then P is this particular polynomial. And define, so I define this map phi from L2 to H, where, so I'm, in this case, I'm viewing elements from L2 as H comma K, so phi of H comma K is equal to the matrix T to the K, 0, 1, and then this by infinite sum minus infinity to infinity of hi t to the I. So h sub I just denotes the bulbs that are turned on in the lamplighter picture for h comma k. And it should be evident this map is well defined. It's a homomorphism. It has a trivial kernel and it's onto. So this is in fact our desired isomorphism. So we can represent L2 as these matrices. And I think it helps with the construction when we're trying to show that the Cayley graph of L2 is isomorphic to our particular kind of Diestel-Leader graph. Okay. So the time left, I should probably define what a Diestel-Leader graph is. So okay. So a Diestel-Leader graph. So consider the following idea. So we consider two infinite trees. Of fixed valence. Let's call it D+1. And we denote these two trees by T1 and T2. or yeah, let's denote them by T1 and T2. Okay. So we orient the trees such in a way that if one has a particular orientation, the other one is flipped upside down. So I'll illustrate what I mean by this. So orient the trees so that each vertex has one incoming edge and D outgoing edges. Okay, so as an example, if I have a tree like this, so so we can call this our T1. And for T2, we orient it in the opposite direction. So it looks like this tree opens up more or less. And then this tree is going to open down. So
Do you need the extra edge at the vertex at the bottom or the top?
We just continue up in that direction, yeah?
yeah. But we're kind of, I think we're zooming in. So when I define this this notion of a height function, I think it'll make more sense.
Okay.
Okay, so for T2, so we have something like this. So T1 and T2 are both, so in this particular case, D is equal to 2. So each vertex has degree 3. And so it has one incoming edge and 2 outgoing edges. And so oh yeah, so I'm gonna fix a height function. So fix the height function. I call it H sub I. So H hat sub I, the domain is going to be T sub I, and it maps to Z on each tree. And so with these height functions, they're actually called Buseman functions. BUS, yeah, okay, Buseman functions. No typo. Okay, so Buseman functions. And so at each vertex, I can assign it a height. So this is not going to be drawn to scale, but something like this. And then I do the same thing for T1. Okay, so for T1, if I label the heights as 2, 1, 0, -1, I label the heights in T2 in the opposite way. So this would be 0, this would be -1, this would be -2, and this would be 1. And if I change the height function for each tree, the resulting tree is still isomorphic. So there's this invariance of height functions we have. So when I mean incoming edge, I mean as with respect to height. So as height increases, each vertex has one incoming edge and 2 outgoing edges. So in this first picture, so if we look at this vertex at 0, it has one incoming edge from -1, or with the vertex starting at height -1, and then the edge goes from -1 to 0, and it has two outgoing edges. And then same thing for T2. So instead, it's oriented the opposite way. So the incoming edge goes from -1 to 0, and the outgoing edges go from 0 to 1. So when we construct this Diestel-Leader graph, it's actually it's a subgraph of T1 cross T2. So vertices in T1s times T2 are of the form T1, T2, where of course T1 is in the first tree and T2 is in the second tree. Okay, and of course I'll just write what I mentioned before. So DL2D. So this is the Diestel-Leader graph. So this 2 is in reference to the number of trees I'm looking at. So if this were 3, I would be looking at the product of 3 trees, each with valence D plus 1. So DL2 of D is a subset T1 time cross T2. Okay, so we actually want to identify the vertices of the Diestel-Leader graph. And we actually have the following idea. So the vertices. So I'll just label this the vertices of the Diestel-Leader graph of 2 trees with valence D plus 1 is the following idea. So it's a set of all ordered pairs, T1, T2, such that their height functions add up to 0. And of course, I should have mentioned that T1 belongs to T1 and then T2 belongs to T2. So in this construction we had right here, vertices in our Diestel-Leader graph are going to be vertices where the sum of the heights are equal to 0. So they're vertices that correspond to the same horizontal layer. So in this case, I have a vertex here and a vertex here. So if I call this vertex S, I call this vertex T, then I have that S and T are going to be the vertex set of the Diestel-Leader graph. So in this case, it would be 2, and then a valence 2, not 3. Okay. So now for edges, we can actually talk about the edges of this graph. So edges. So if I'm given S0, T0, and S1, T1, and these are vertices in my Diestel-Leader graph with respect to 2 trees of valence D. They are connected by an edge. So I'll use this in notation of S0 is connected to S1 and T0 is connected to T1. So if each corresponding pair of vertices in the respective tree, so if S0 and S1 are connected in T1 and T0 and T1 are connected in the tree T2, then the ordered pair at S0, T0 and S1, T1 are connected in the Diestel-Leader graph. Okay.
So could you go back up to the picture then really quick?
Oh yeah, sure.
So okay, so for example, that S and T is a pair it's a vertex in the graph.
Mhm.
And if I were to pick something else on the same level, I guess. So another S in T1 and another T in T2.
Mhm.
That counts as a vertex, or there would be an edge between those two, I think. Did I read that correctly? Or
Yeah. So S and T, or so S comma T are a vertex
that's
in
one. Yeah.
Diestel-Leader graph. So if I take, for example, S prime and T prime.
Just one level.
So
Okay.
yeah. So the height functions with respect to S prime and T prime add up to 0 because they're both on the layer 0. So they're both a vertex in the Diestel-Leader graph, or yeah, the pair S prime T prime are a pair in the Diestel-Leader graph, and S is connected to S prime and T is connected to T prime. So this would this would correspond to an edge in the Diestel-Leader graph.
Okay. Okay. Thanks.
Okay. So with given the time I have left, I might as well just skip to the punchline. So this is a good theorem. And the theorem states that the Cayley graph with respect to L2 and the generating set. So in the generating set I defined above, I used A and T, but in this generating set, it's actually T and AT. This is graph isomorphic to the Diestel-Leader graph of two trees, each with valence 3, so 2. And this is the big idea. So if these two are isomorphic, then the Diestel-Leader graph of two trees, each with valence 3, is at least going to be quasi-isometric to the Cayley graph of L2 with respect to any finite generating set. And because of this, this is our main example. We took this really nice graph, or somewhat nice, depends on what you define as nice. But and we defined it as nice in our context. This Diestel-Leader graph of two trees with each with valence 3. It's a nice infinite graph, and we showed it's quasi-isometric to the Cayley graph of L2, which is not finitely presented. So we have our nice counterexample. And I want to make, with a few remaining minutes I have left, some comments on these Diestel-Leader graphs. So the construction I took with the two trees is actually what is known in literature as a horocyclic product. So I view these trees in the symmetric space setting, and I consider vertices of this form. So their height functions, the vertices in each tree, the evaluated with the height function sum up to 0, and the edges corresponding in this way. I actually get a horocyclic product. And then each of the horizontal layers in the picture, so each layer is a horocycle. So this notion of a horocyclic product extends beyond trees. You can take it with hyperbolic planes, I believe, and you can also take it with something else that I forgot on top of my head. So this construction of the Diestel-Leader graphs, these graphs are actually very cool to play with. There's a bunch of literature that talks about random blocks on these graphs. You can do analysis on these graphs, so solving the Laplace equation on a Diestel-Leader graph. You can consider analytic functions on this Diestel-Leader graph, and so on. Yes,
Your
sorry.
references for the papers on that? I'd like to play around with them.
So let's see. So I think if you look at Woess, so W. Woess, he has a few papers published on doing analysis on these graphs. There's other authors that also play around with this idea, but I can't remember them on the top of my head.
It's on archive though, probably.
It should be, yeah.
Okay. So this guy's okay. I think I found something. This guy is what? Woess is. How would you define him? Is he analyst or is he geometric group theorist or what is he?
So geometric group theorist, he does a lot of his contributions are, I guess, more geared towards discrete math, but he also plays around with ideas of an analysis.
Okay, I see a couple mentionings of things here. Cool. Thanks.
Yeah, so that's all I had to say today.
Okay, cool. So then with that being said, let's thank our speaker really quick.
Yep, thank you.
There's like a clapping button. Now I do that. So any questions from the audience? If not, I might have like one more. So people doing analysis on these graphs, is there a particular reason? Like what kind of things are they looking for, I guess? Or what's, because analysis, I know a little bit about spectral theory on graphs, which is the closest thing I know to analysis on graphs, but it's all for finite, or in the finite case, I guess. So what, I guess, what's interesting, what kind of project, or I guess topics are these people looking into? Do you know?
So I'm actually reading on that now, but I'm not too particularly sure. I guess it's working with the discrete setting. So I at least know for random walks, when you talk about random walks on graphs, they're more interesting because instead of, say, when you're taking a random walk in Z2, you're working with this particular structure, but when you're working with a random walk in graphs, you have this notion of there's different degrees at every vertex. So the walk becomes more interesting, and your initial conditions for random walk on this graph could highly affect the results on when you like study asymptotics on this, but I'm not too sure. I'm actually looking into this topic right now.
Okay, that's interesting. So is it infinite graphs that these random walks are happening on, or finite graphs? Or
usually the interesting results come from infinite graphs.
okay, cool. So we should talk at some point. That's interesting.
Yeah.
Okay. Any other questions from the audience? If not, let's thank our speaker one more time. Thanks again. That was a great talk, I think.
Thank you.
Let me stop recording.